want to talk about something that I've been implementing recently, and that's called domain coloring. So it's a really interesting way of being able to visualize functions of a complex variable. And I think just to sort of ease into it, I want to sort of talk a little bit, just very briefly, about the general philosophy of visualizing things. Right? So the thing that we learn most earliest is graphing a function like this. So we have a single real input and a single real output. And there's sort of two dimensions of information here, which is why we plot it on a nice 2D graph like this. So we have x being the input and y being the value of the function at that point. That's pretty straightforward. Now, when we get into higher and higher dimensions, things get harder. So here I have a horrible graph of f of x, y. So now this is a sort of a function or a graph with 3 dimensions of information, x, y, and here. And I've drawn some level curves. This is like sort of like a topological map, like if you've ever seen. Basically, you just draw circles for points of constant of the same elevation. And so you can deduce some information about this and get the idea that, you know, for example, because these circles are getting closer together, this function is increasing more rapidly as you get away from the center. And in that same vein, we can also make a 3D graph. So even though this is projected onto 2D space, we're generally pretty good at interpreting even horrible looking graphs like this one. Then if you have 4 dimensions, things get maybe a bit trickier. A very common case of this is when you have a vector field. So you have a 2D input and some output. I don't know what function this is, but it doesn't really matter. The point is that you associate to a bunch of points in your domain some arrows. And the length of the arrow and the direction tell you the output. So this is great. The question is, what's the best choice that we have for some complex function, right? So what's the best? Obviously, this has 4 dimensions. There's 4. It has 2 complex number dimensions, but it has 4 real dimensions, and it also has 4 topological dimensions. So this vector field would work. We could draw a complex number that way, but there's an even better way to do it, and it's better in most cases, and that's something called domain coloring. It's a little bit more subtle than these. These, I think, are quite intuitive. Domain coloring is a little bit more subtle, but it's, in my opinion, just incredible. And what it does is it uses a dimension of perception that we don't normally think about, and that's color. So all of these, the color doesn't matter to them. But with domain coloring, we actually associate the color of a point with information about that point. And we'll see how that works in a little bit. So what we're basically looking to do here is to find a nice function that takes in a complex number and returns a color that we can see, and then associate to each point in our graph that color. So a fairly natural way to do this is to use something called HSL, which is hue, saturation, luminance. And this is a color model that's a little bit closer to how humans actually perceive color. So hue is something like the position of the color wheel. Saturation is something we don't have to talk about in this case. And luminance is how bright it is. So this is a plot of that actual coloring function. So you can see at 0, it's black. We have the luminance set to 0 when the magnitude is close to 0. And then as we get further away, it gets brighter. So the luminance increases, and the hue is determined by the angle that that point makes with the origin. Note that by convention, we start with green as the positive real axis. So to be quite explicit, we have this formula. So the hue is the argument of the complex number, which is the angle it makes with the positive x-axis, plus 2 pi over 3, just so that the positive x-axis is green. Saturation we just set identically to 1, and the luminance we set to some function of the magnitude of the complex number. Now this choice of function is somewhat arbitrary, but it just has to have the property that it takes numbers from 0 to infinity and somehow maps them into 0 to 1, because luminance is between 0 to 1. So here's what it looks like fully applied. So we have a function of a complex number which associates to each point in the complex plane another complex number, and then we convert that into a color which we display, and that color function is the function that we just described. So here is an example function z squared minus 1. You can see that for positive real numbers, there's 2 roots here, so -1 and 1, which is where that function is equal to 0. For positive real numbers, so for example z equals 2, we have 2 squared minus 1 is 3, and indeed it's green here, so a positive real number. And then for real numbers between -1 and 1, which is this region here in between the roots, we have a negative value. So for example, 0 squared minus 1 is -1, so that's negative. And this graph now tells us also about the behavior of other numbers applied to this function. So if we look at these roots and we traverse them counterclockwise,
we see that we pass through all the hues in the color wheel. So we start here on the right of this root 1 as a positive real, and then we go from green to aqua to blue to pink, which is negative real, and then to red and yellow and back to green. So as we traverse these roots in a counterclockwise direction, we go all around the color wheel, and same is true for negative 1 here. So now we can look at a slightly less intuitive function, z squared plus 1, and now this has roots no longer on the real axis, but it does have roots in the complex domain. So plus I and negative I are the roots here, and we can see that they're colored black. And again, we have similar properties to the first one. As we traverse them counterclockwise, we go around the color wheel. So this is quite cool. We can understand quite a few new functions this way. But one problem that this has is it doesn't deal with the sort of the vast range of complex numbers that are often outputted, because the luminance function that we have can only range between 0 and 1, and so it's hard to find a nice function that maps between the complex numbers or the possible magnitudes into that very limited range. Because complex numbers, they often go very quickly to 0, they blow up in the expressions we're considering. So here's e to the z, for example. E to the z is periodic with period 2 pi in the imaginary direction, but as we know, just considering the real axis, it blows up to infinity very quickly as x goes to infinity, and it goes to 0 very quickly as x goes to negative infinity. So we can't really get much understanding of what's going on because everything just becomes white. And especially if we zoom out, it's just black on the left and white on the right, and yes, there's this area that we understand in the middle, that it's periodic. But we can't really see the stuff on the white. So one nice solution to this conundrum is to change the function that we're using from the magnitude to the luminance. In particular, we relax the restriction that it's monotonically increasing, and we actually use a discontinuous function. So we have magnitude 0, we just have it be 0, but for other values of the magnitude, we have this coloring scheme that, or this brightness scheme that scales sort of exponentially. So we get a sort of varying resolution. When m is very large, we have a less absolute resolution, but when m is very small, we have very high absolute resolution. So this is what our new coloring function looks like. As you can see now, it no longer associates a unique magnitude with a unique luminance. But it does have this property where when we get close to the origin, when the magnitude becomes really small, we repeat ourselves, basically. We start reusing the same luminance, and this allows us to have greater precision in those areas. Now, these very sharp color changes are a little unsightly, so we actually scale the luminance into a more reasonable range. I think I used 0.3 to 0.8 here. So now we should learn how to interpret this graph. Importantly, the function is not discontinuous where we have these edges. That's just where the function's magnitude crosses a power of the base we're using. In this case, I'm using base 2. So there's a circle at a radii of 1, 0.5, 0.25, and a 2, 4, etc. Now, this property means that we have to take some care as to whether a point is a pole or a 0. So a pole is a point in a complex function which sort of blows up to infinity. Whereas a 0 is where it goes to 0. But because we have these concentrated circles that are every power of 2, they sort of look very similar. And so you have to be careful which one it is. The way to tell is that as you're approaching a pole, the luminance should still be increasing between each jump, whereas as you're approaching a 0, the luminance will be decreasing before you get to a jump. So we can explore these plots a little bit. So this is the function I was just showing. This is 1 over z minus 1. So 1 over z blows up to infinity at z equals 0, which is why we have a pole at z equals 0. And it's equal to 0 when z equals 1. So that's what we have, the 0 at z equals 1. Well, that was a tongue twister. So this is nice. We have an example of a pole and a 0 next to each other. 1 over z by itself, just as a single pole, makes sense. 1 over z, or actually let's look at z squared. This is something interesting here. So we start as positive, and then we go around, and we get to the negative real axis, and we get a positive result, which makes sense, because when we put in negative 3 squared, for example, we get 9, which is a positive real number, so it's green. And so as we traverse a circle in the input space, we go around the output twice. So we can actually show a circle here. change the race a little bit. This gray point is a point of the input, and this yellow point is the actual output for that gray point. As you can see, every time the gray point goes around once, this yellow point actually goes around twice. And this generalizes. So for example, if we have z to the 4, I'll change the race a little bit here. The gray point goes around once, and the yellow point goes around 4 times. So this is a sort of fundamental property of raising a complex number to an nth power. Another cool thing is, let me turn these circles off, the graph of e to the z. I'll go back to that. Can zoom out a little bit, and you can see it looks very different than the graph we had earlier. That's because we're now able to graph a larger dynamic range of magnitudes. So you can see here we have these very evenly spaced lines, and that's because e to the z goes up exponentially as we go from left to right, as the real part goes from very small to very large, and thus we'd expect to have these evenly spaced discontinuities, because that's exactly how we're coloring it. We're coloring it between 2 to the negative 5 and 2 to the negative 4, just as we're coloring it between 2 to the negative 4 and 2 to the negative 3. And as sort of a consequence of this, if we consider something like cosine of z, we have these zeros here at what, pi, 3 pi, etc. But we also have this exponential behavior coming away from the real axis.
Common misconception in complex analysis, certainly for me, I fell for this, is that cosine and sine, the trigonometric functions, are periodic in both directions. So cosine is indeed periodic in the real direction, because there's pi and 3 pi, and in general, cosine z plus 2 pi is indeed cosine of z. It's periodic in this direction. I also thought it was periodic in this direction. So I thought that there'd be a root here and a root here, etc. No. Cosine and sine and all that do not behave like that. In fact, if we go back to the definition of cosine, skip this if this is obvious to you, but typically is how we define it in terms of complex exponentials. And if we let z equals I times w, where w is a large positive number, right? Then cosine of z becomes approximately e to the I squared times w plus e to the negative I squared times w over 2. This becomes negative w. This becomes positive w. And this is tiny. This becomes huge. And so this is about e to the w over 2. So, in conclusion, as w gets large in imaginary value, this blows up. So cosine is huge over here. It grows exponentially. And similarly, the other term here, when w becomes very small negative number, very large in this direction, then this dominates here. So it's huge here. Basically, cosine is a valley. So there's this interesting behavior here where it has these roots and whatever, and then here it just blows up to infinity exponentially. And we actually see this in the graph.
You can tell that it's exponential by the fact that the lines are equally spaced. So cosine of z becomes exponential as you go in the positive and the negative imaginary directions.
So another cool thing that I really like this for is understanding the fundamental theorem of algebra. So that theorem, I mean, there's various equivalent forms, but sort of the most simple form is that given any complex polynomial, so this is some complex polynomial, if this is non-constant, then we'll have some z0 which satisfies p of z0 equals 0. There's some root of this polynomial. And furthermore, more stronger forms of this are able to conclude that there are n roots, including multiplicity. It's not obvious, right? Because there's all kinds of functions in the real numbers that don't satisfy this property, right? Here, the easiest one being z squared plus 1. This has no roots in real numbers, but in the complex numbers it has plus or minus I. So why is this true? Okay? The answer is very beautiful. I mean, there's many proofs, and this one is particularly formal. Can be formalized. Maybe I'll do that later. But suppose we have z, the parameterization of the unit circle. So we're sort of examining values of z confined to the unit circle. So like here, it says radius r, and so we'll let theta vary like so, right? So theta will traverse the circle here with radius r like this. And then let's consider the image of the circle under P. So what do these values look like? If R is large, if we take R large, then remember that R e to I theta to the power n is this. Now the magnitude of this is 1, and this, if R is large, this grows very quickly, and more importantly, this is going to eventually become greater than the next term. So if this is our first term here, a0 or whatever, then it's eventually going to be much greater than our next term here. So put that here. Right? So this term is eventually going to dominate all these terms for R large. So R being large implies that P of z will become approximately a0 times z to the n. 0. And if we think about this, what this really is, we write this out. This is a parameterization of a circle going around the origin of radius a0 times r to the n, but traversing it n times. So we start here, and we traverse it n times, because the exponent is n here, right? We're going from theta equals 0 to 2 pi. So the input here goes around here once, and the output here goes around n times. So that's the image of a circle for R large. Now, this is our analysis for R large. What happens if R is small, right? If R is very small, then we sort of have the opposite behavior here, where all these terms go to 0, and we'll just get something like P of z is about the constant term. So let's suppose the constant term is here. This is an. Then the image of our little circle around the origin of radius r is going to look like a little circle around the constant term, or a little contour on the constant term. And what this means, if we look at both of these, we know that because polynomials are continuous, if we take this large input circle and we squish it down to a small input circle, the output must also be a continuous mapping. There must be, I don't know if there was a homotopy, but whatever, like a way to take this large image and contract it to the small image. If you think about it, what that means is this large image has to pass through the origin, because this image has to go here, and then contract to an here. And in that process, it will necessarily intersect the origin. And, assuming the roots are distinct, it will intersect the origin n distinct times, because it's going around the origin n times. So this is not super formal, but it's a really cool way to understand the fundamental theorem of algebra as the necessary behavior of a curve contracting to a point.
So for the natural question is, where do we go from here? So obviously one thing to do just to make the graph faster. It's already pretty good. So here's cosine z over 1 plus z squared. You can see it takes 380 milliseconds for, I think it's 750 by 750. So we can calculate that. This is not too bad. And for super simple expressions, it's really fast. In fact, most of the time is spent in the domain coloring function. So there are some functions where it's a bit more expensive, like gamma of z isn't particularly optimized yet, but it's not bad. And of course, I want to get a better interface than this piece of shit. You can only zoom on 0, 0, and you can't really, it's just not very ergonomic. I can't drag around here. And that's not because of some, it's just not, it's immensely difficult. It's just I haven't implemented it yet. But more importantly, I want to be able to integrate this coloring into other types of graphs. It'd be really cool to have a 3D graph of a complex function, so like that 3D graph that I showed at the beginning of the video, but coloring the 3D graph according to the domain coloring as well. So that way you have both the visual of the 3D growth and the coloring that tells you the argument of the complex number at various points.